Okay, let's go for the last topic for this chapter 29. It's gonna be motional EMF. In this case, we have a conductor that changes the area inside of a magnetic field. Imagine at the beginning we have a conductor right here and then moves to this position, and that happens because we apply a force. So the conductor is moving with some velocity v. Perfect. Now let's see what happens when we have a charge moving in a magnetic field. We know that if the charge moves to the right with this velocity, if we use the right hand rule, this charge experiences a force, right, which is perpendicular to the velocity of the particle and perpendicular to the magnetic field. In this case, this is the velocity of the particle, this is the magnetic field going into the wall, right? So the force is perpendicular, so it's gonna be in this direction. And that's presented right here, right? All the charges, and remember the charges that moves are the positive charges when we're dealing with conventional conditions, right? So the positive charges moves, let's say, to this part, correct? So this remains negative. So what happens when we create potential difference, right? We induce a electromotive force in this case. Perfect. Now, what happens when we have the conductor and we have a current, right? Because right here we have a current through the conductor. Then one more time it's found that we have a current, right? This conductor inside of a external magnetic field, a force is present, correct? And that force again is found using the right hand rule. If we have the current in this direction, the magnetic field in that direction, right, the force that is done on this conductor or wire is equals to in this direction, correct? Then we found this force, right? This force is equals to what? This force must be equals to the charge times the magnetic field, right, times velocity times sine theta. We found that before. Okay, great. Now, and this is the force represented in this figure. Perfect. Now, we mentioned that a potential difference is created. We have an electromotive force. Perfect. Now, let's see what happens. Remember, we're dealing with electromotive force, and we mentioned that one of the ways how we can break electromotive force is when we change the area of a conductor inside of a magnetic field. And to do that, we applied the Faraday's law that we found before, is minus n, numbers of loops, times the change of the magnetic flux, right, divided by the time. Okay, perfect. Now let's do it right here. Let's try to find the formula that relates the electromotive force and the change area in this conductor, in this circuit. Perfect. We know also that the magnetic flux is found to be the magnetic field times the area times cosine theta. The angle right here is the angle between the magnetic field and the area as a vector. We explained that before, right? So there has magnitude, has a vector. In this case, the direction of the magnetic field and the area goes right into the wall, means that these two are parallel. If these two are parallel, these two vectors, so the angle is 0. If the angle is 0 right here, cosine is gonna be 1. Perfect. Now, in this picture, right, the magnetic field is constant, so the quantity that is changing is the area. In this case, we have that electromotive force is equals to negative magnetic field times the changing area right with respect to time. But how there is changing? Well, we found it right here. The area is, or the changing area is equals to L delta x. Well, delta x is V delta t. Perfect. Now, when we substitute the value right here, what do we have? The change in the area is equals to LV delta t. Or we can use small changes, and we can represent this also in this way. The area is equals to LV dt. The same idea. Perfect. Let's substitute then this value right here, and what do we have? This is B times LV dt over dt. And at the end, this is equals to negative B LV. Perfect. And this is the motional EMF equals to negative BLV. Correct? Now let's try to create a generic equation using also this formula that we found before. Correct? And as we know, this can be represented in this way too. Now as a vector is kind of magnitude, right? Let's make this as a vector, and that'll be charge times the product of V cross B. Correct? Perfect. Now let's relate this the force with the electromotive force. Okay, let's do it. We know the electromotive force is defined as the work done, right, divided by the charge. But how do we define work? Work is equals to force, right? L, that L, or the displacement right here. Perfect. Now divided by the charge. But what is the force in this analysis? It's gonna be charge, right, times this cross product divided by the charge. And that L. Perfect. And then what do we have? Is equals to this cross product, right? That L. Okay, now we can also use integers, right? Because we're dealing with closed path. In this case, we can represent the electromotive force as the integral through this closed path of this product. V cross B, that's dl. Right, that's dl. Okay, great. And this is another, these two are the same. As you can see, these two are the same. Right, they have the same form. This is using integral, this is just using just the magnitude. Okay, so again, it's another way how we can represent the motional EMF. In this way, the integral, right, of this product. Perfect. Now, this is the force done on the charge because of the magnetic field. What about if we add also the force on this charge because of the electric field? Remember, we're creating a potential difference. Now, let's invoke also that force to create a general equation. Okay, let's do it. And when we do that, remember, we create the Lorentz force. We're working with the Lorentz force, the total force acting on a charged particle. Okay, let's do it. Let's do it. So we have the Lorentz force, right? And that's the net force, right? The net force acting on a charged particle, okay, is equals to this charge times the electric field plus this product, correct? This is the total force acting on the charge. Now let's repeat the step as we did before. We are now applying the electromotive force is equals to work done divided by charge equals to F, right? That L, right, divided by the charge. And when we do this process, right, we get something like right here, right? We get the equation that the electromotive force now is equals to the integral of this electric field plus this cross product, that's the L. Right, we just add to this force the electric field, right? And we create the same formula, right? We follow the same steps as before. Okay, perfect. Now, we found that this term right here is this one right here, and this is the motional EMF. What about this one? The electric field. What about this one? The closed integral of the electric field, that's the L. How this is produced? How we can involve or relate this to the electromotive force? Well, in this way. We mentioned that when the velocity is involved means that the area is changing. And we take for simplicity the magnetic fields to be constant. Now let's do the opposite, right? Let's take the area to be fixed, and we increase the, imagine this is the area over here, could be any loop, right? And we increase the magnetic field, right? Let's see what happens when we increase the magnetic field. Well, if we increase the magnetic field through this loop, correct? Imagine it goes in this direction, or the classical way, right? Imagine that we have this magnet north-south, right? And we have this loop right here, and the magnet moves down. Well, at this point, right, the magnetic field is increasing. Imagine something like that's happening right here. Okay, now means that we have a change in the magnetic flux, right? How do we define the magnetic flux one more time? Well, it's coming using this equation number 2, correct? This equals to what? B area cosine theta. But right here we're dealing with a change, right? We have a change on this magnetic flux. We found one more time, or we established that the area is constant. Cosine, remember cosine of the angle is the angle between magnetic field and the area, imagine, parallel. They're gonna be 0, so we are dealing only with these two quantities. Okay, but the area is constant, so this is equals to what? This is equals to magnetic fields times the change in area. No, we had it before, no, the area is constant. This is gonna be the opposite. The area is constant, so we have the change, okay, area is constant, change in the magnetic field. Right, now let's apply the condition for the electromotive force. We know that the electromotive force is defined according to Faraday's law, right? Negative this change, because we're dealing with one loop, right? Magnetic flux is divided by time, so it's equals to what? Area, right? dV dt negative, correct? But we found that this is, right, the electromotive force, so this one must be equals to what? So it must be equals to negative area dV right dt. So this induced electric field is produced because of the change in time of the magnetic field. We explained that before. For example, oops, for example, let me erase this part right here. For example, if we have a magnetic field, right, that increases, magnetic field increase, it produces or induces a electric field, right? And this is established by this relationship, right? This induced electric field is due because of the change in the magnetic fields in time, and this two is found to be perpendicular. Perfect. So we found this relationship, that this induced electric field is equals to negative A, right, the change in the magnetic field. Correct? Perfect. Now let's go to the next topic. The next topic is gonna be the dynamo, the Faraday dynamo. Okay, let's do it. Let's go to the dynamo. Right? This is the Faraday disk dynamo. The Faraday, okay, oops. Faraday disk dynamo. Okay, perfect. Imagine that we have this magnetic field, correct? It's a magnetic field, and we have this conductor, correct? This conductor, and this conductor has this angular velocity. This is solid, it's a disk, correct? Imagine that this is the center, and we have a segment right here, correct? Aligned, perfect. And let's take only one particle, one section right here, Imagine this produces this path right here, and it has this velocity, right? It rotates. Perfect. Now we know that velocity, right, is equals to r, right, times omega. Perfect. Now remember we're dealing with motion on EMF because it's moving. We have change in velocity, so we need to apply this equation number 4 or number 5. Okay, let's use number 5. So means that we're looking for this product, right? And this product too. Perfect. What should be in this picture? B cross B. Okay, well, let's take the magnitude is equals to V times B. Perfect. Now, what should be in this formula? This dl, well, this L is gonna be just dr. Correct? Perfect. Maybe this is dl assignment right here. This is dl, this is dr because rotating is gonna be r or r, right? Or big R. Okay, great. Now let's go to the electromotive force. Then is equals to, according to motional EMF, the integral of V cross B, correct? That the L is equals to what? This is equals to the integral of B, right, times, what is B in this case? Because we found this product, right, which is this one, B, but V is equals to R omega. So now V then R omega, what else? R omega B. Now this product is gonna be dr. From where to where? From 0, right? This is the whole. This is R, right? This is R, little r, and this is big R. Okay, from 0 to R. And what is this? This is equals to R. Are gonna be B omega omega, right? B omega R squared divided by 2. But which R is this one? Gonna be big R, correct? Big R squared divided by 2. Right, and this is the electromotive force, right? That is created when we have a solid disk, right? Rotating inside of a magnetic field. It's coming by this equation. Perfect. Magnetic field. This is the electromotive force. Electromotive force equals to magnetic field omega R squared divided by 2. Correct. Perfect. Now let's go for the next topic. The next topic is gonna be displacement current. The displacement current. Let's explain this current. Let's do it. Let's do it. Displacement current. Displacement current. Okay. Look, imagine that we have a capacitor, right? We have a capacitor right here. Imagine this is the capacitor. We have this part. Oops. We have. Let me make another. Again, it's gonna be this. Oops. Oh my God! What happens? What happens? One more time. I have to do more carefully. Okay, more carefully like this. Perfect. Oh my God! I did it. Okay. Okay. Perfect. And imagine that this is connected to a battery. Correct. Let's take this picture again. We have these two plates. Where we have a battery right here, we connect to a battery. Perfect. When this is open, the circuit is open, what happens when we close it? Just after we close it, right? We close the circuit. We have right here, right, current going in this direction, right? And we have, of course, the creation of the magnetic field. The same thing happens in the other side, right? Right here we have current right, in this direction. So we have a magnetic field, right? But what happens in between, right? Look, at the beginning, this plate is being charged, right? And it looks like the charges goes from here to here, because in the other side also we have charge, we have current, right, moving, right, and creates a circle, right? Perfect. But what is happening right here? We don't have charges. See, what do we have in between? An electric field, right? In between we have an electric field. And this electric field is increasing, right? So we have a charge coming, and then we have the creation of this potential difference right here, right? And we have current in the other side too. That happens at the beginning, right? Later, when it becomes charged, there is no more current, but we have an electric field. But at the beginning, the electric field is zero, and then goes from zero to some amount, final quantity, right? So means that the electric field is changing. And we know that when an electric field changes, or in this case increases, a creation of the magnetic field is created. A magnetic field is created. Remember that part? Remember this part when we have a electric field that increases, right? We have a magnetic field. Or the opposite, if we have a magnetic field that increases, we have, right, an induced electric field. Correct? Now what happens right here? Right here we have that the electric field is increasing, so we have the creation of a magnetic field, right? Magnetic field. This is the electric field. Correct? That's the main idea. Great. Now let's see how this part is related to this part. Well, in these two sides we have the magnetic field. We know this is equals to mu naught current divided by 2 pi r. Right? This is found right here, right, and right here in these two parts. But what happens in between? In between we don't have charge. Right? We don't have charge. How this is created? Well, let's do it. This is the idea. One more time. At the beginning, right, we have charge, and it looks like the charge goes inside of this empty space, right, and go to the other side, and the current continues, right? That's the idea. But as we know, right here we don't have charge. The charges start from here to start right here, and then continue right from here to the other part of the circuit. Okay. Now, how we can explain that condition? Well, we can make the idea that actually this part at the beginning is continuous. At the beginning also we have charges coming, goes in between, right, and complete that circuit. That's the idea. Okay, now let's explain this part. How the charge goes from here to here? Well, we call that the displacement current. Correct? And this is found in this way. That was explained by Maxwell. Okay, Maxwell. Now imagine that we have, because right here we have an electric field, and the electric field is increasing, so means that we have a electric flux, right? And the electric flux, we have a change of the electric flux also. So the electric flux is defined as the electric field times the area times cosine theta. And before, the same thing as before, right? The angle is 0, and we have only the electric field times the area. The angle is 0, so cosine is 1, so we have the electric field times the area. Okay, perfect. What about the electric field between these two plates? Remember, we found the electric field is equals to sigma divided by epsilon naught. What is sigma? Sigma is charge divided by area. So we have charge divided by area epsilon naught. Perfect. So this is the electric flux. It's gonna be what else? It's gonna be when we substitute the values, it's gonna be charge over area epsilon naught times the area is equals to charge divided by epsilon naught. Correct? Now let's apply the change, the idea of change. Okay, so we have now the change of this electric field is equals to the change of the charge, right, epsilon naught. But now let's do this change respect to time. Okay, respect to time. Okay, respect to time. And what do we have? Okay, if we do this respect to time, this is equals to respect to time, right, and 1 epsilon naught. But what is this? This is current, right? We have a current that is induced, let's say, in between, and we call that the displacement current, correct? We have a current, according to this equation, this analysis, correct? We have a current that is produced. One more time, this is now the change of the electric field with respect to time is equals to this current. We call this current displacement because we don't have current inside. We don't have a solid current, right? That is the induced that is sent from here to here to continue this path. Perfect. So divided by epsilon naught. Correct. Perfect. Now what else do we have? Right here we can substitute, solve for the displacement current. HD is equals to epsilon naught times this electric flux, right? Change the magnetic flux with respect to time. Okay, great. Now this is the current that we expect to have in between these two plates, and we follow the same pattern as right here. If this is the current right here and right here, it should be the magnetic field. Now right here we have the magnetic field is equals to mu naught times this displacement current divided by 2 pi r. The same meaning, the same idea. Correct? Perfect. Now let's go. Well, this is the analysis for displacement current. Correct? The displacement current is found to be equals to the epsilon naught times this change in the electric flux with respect to time. Correct? Perfect. And now this is involves or is added to this equation, right? And this is part of the Maxwell's equations. Okay, great. Now finally, let's go to create all this the conclusion for this chapter, right? And this is the Maxwell equations. Okay, let's do it. Maxwell equation. Maxwell equation will involve this quantity, right? The displacement current, which is again introduced by Maxwell. And it will help us again to find the speed of light. It's a very important quantity. Okay, perfect. Now these are the Maxwell equations. Maxwell, right, equations. We have the first one. This is actually Gauss, right, which is the integral, right, of the electric field. That area is equals to magnetic flux divided by epsilon naught. Correct? We have another one, also from Gauss, and this is the integral of this product is equals to 0. Also we have Faraday's law which says the integral of E, right, the electric field that the L is equals to negative, we just found it before, right? It's gonna be this over here. It's equals to negative the change of the magnetic field respect to time, which is the same as this one that we used before. Okay, and finally we have the Ampere Maxwell, right, equation which says that the integral in this closed path of B magnetic field that the L is equals to this mu naught times current plus the displacement current, correct? And this is equals to mu naught times current plus this quantity that we found before, right? Epsilon naught change in the electric field, correct, respect to time. Perfect. And these are again the Maxwell equations, are very famous equations. It's actually a summary of the previous laws that we found before for Gauss's, Faraday's, right, and Ampere. Okay, great. With this we finish chapter 29, right? We conclude the electromagnetic induction. It's a very important chapter, correct? And see you in the next chapter. Thank you. Bye.